Hello everyone, today we'll talk about the problem create binary tree from descriptions. We're given the descriptions which say that the node with value parent of I is the parent of the node with value child of I, and we're also told if that child is a left child or a right child. So we have those triples of values, list of those triples. We are guaranteed that this is a valid binary tree, and we have to return it, specifically return its root. Maybe the thing we should start with is to convince ourselves that this list of descriptions is enough to reconstruct a tree in a unique manner. We know that for a general graph, a list of pairs, it wouldn't be parent-child, it would just be node and node. But a list of pairs, so a list of edges, is enough to identify a graph, a unique graph. Because in general, a graph does not have any notion of an order when it comes to its neighbors. And here we have, of course, a tree is also a graph, so it's possible to reconstruct a tree as well. If we want to consider a tree to be rooted, then we just might think about that tree as a rooted tree, a rooted graph, such that all the edges point away from the root. And then again, it would be like parent and child in this case, so that's also okay. And for our case, where the tree is binary, then there is also a notion of a left and right child. And now every node connects a parent to a child. So all the edges can be separated or colored into two colors, where one color is for the left edges and the other is for the right edges. So when you take a tree, you color left edges one color, right edges another color, then by specifying the list of edges, by putting the parent on as the first value, child as the second value, you indeed keep the tree rooted as it was supposed to be, and you also have to give the color of the edge the direction. So indeed it's enough to reconstruct a tree. And how do we do it? There are multiple ways. There are some ways that will explicitly convert our tree to a graph in some representation, either the most general representation as an adjacency list, maybe as a list of parents for every node. But there's also a simpler solution, and that will be the solution that I'm going to present today. I also think that it's the most intuitive solution. One more thing that we have to make sure that we understand before we jump into the solution is that we have to return the root of the tree. And of course it makes sense, because the only way we can traverse a tree without any auxiliary data structures, an auxiliary stack, or without threading the tree, so changing the links in any way, is we have to have a root. We cannot go up the tree. So it's important to return that root. And how do we identify a root? Because here, of course, we're not told what the root is. So when we have a tree that's rooted, so we may imagine that it's directed downwards, and so on. Then, well, this is a weird face, so maybe let's remove it. So how do we identify a root in this case? Well, we know how to identify roots and leaves, well, the single root and leaves, easily. A leaf is something that has no children. So a root is the opposite of that. It's what has no parent. So if we just keep track of all the nodes that have parents, there will be one node that doesn't have a parent, because we're told that this will be valid. And that node will be the root that we'll have to return. So let's see the solution. We will be maintaining the set of all the nodes that have parents, so that appear as a child in some instance in our description. And we'll also be maintaining a mapping from node values, which are unique in this case because they are the identifiers, to the node objects, because we have to create a tree that's, in an object-oriented representation that has objects that point to other objects. And we go through our descriptions. We make sure that parent and child have already their nodes created, otherwise, because if they don't, we just have to create those nodes with appropriate values. We remember those nodes, so we just look up them in the dictionary in our hash map. And now we know that the child has a parent, so we add it to a set. Of course, a set holds no duplicates. And we set the child of the parent node appropriately. If isLeft is true, that's a left child, otherwise it's a right child. And after all that remains is to return the root. One way we can do that is that since we have a set of all the nodes that have a parent, we also have a set of all the nodes. That's just all the keys in our nodes dictionary. So we convert them to a set. Now we can subtract one set from another to take everything that's on the left-hand side, but not on the right-hand side. We take any element from that set, because there will be exactly one element and it will be a root, because the tree is valid. And that's the identifier of the root node. So we have to return the node corresponding to that identifier, and that is the whole solution.